Pacific Islands, that's about it.
Are you recording?
I am.
Okay, Kevin, be quiet. So we did ours on Slinkies. No, just kidding. So basically we just wanted to understand why when you hold a Slinky up and let go of the top, the bottom doesn't move. And we thought that the bottom would accelerate at 0 and that the top of the Slinky would be moving faster than gravity. We thought that the center of the Slinky would be moving around 9.81 meters per second.
Because there was people on YouTube that said the center should move around 9.81.
Right.
That's the center of mass, which is actually not that one. It's this one.
Yeah. So basically, we thought that the whole Slinky would kind of be compressing throughout the fall, but we were wrong. Nothing on the Slinky moves until the top hits it. So it's like information being sent down. Nothing knows. No part of the Slinky knows that it's falling until the top hits it. So what we did was we just marked the top, the bottom, the middle, and then the 2 points in between them on the Slinky, and we videotaped it falling, and then we made this graph of position versus time. So you can kind of see it just from the graph, that right when we drop it, nothing moves, and then no point on it really moves until the top has come down.
These are completely flat.
So, and then the bottom point doesn't move at all. So we stopped it right when the top hits the bottom. And then this is the velocity graph. So this is the top point. It goes top to bottom, going up. So this one got kind of messed up just because of Logger Pro. It was getting confused by how small changes and graphing really, really small changes. But basically, there shouldn't be any velocity until it gets hit by the top. And the top's velocity is kind of confusing because it would start going down negative, and then it went up again, and it was really confusing, but we noticed that it wasn't until it passed through the center of mass that it started changing direction.
Right about here.
And so then acceleration versus time is really confusing, but basically the Slinky it had a negative acceleration at the top, and it was faster than 9.81, but it slowed down significantly once it hit the middle and went to a really positive acceleration. And we thought it was because there was a lot less tension in the bottom half than there was in the top half, and so it was slowing down significantly once it passed through that center point.
So why does like the second, the brown line, why does that get faster than the original?
We don't really know. We think it's because of the Logger Pro.
Either that or the momentum of the top hitting it, I think.
I know that you said that none of them were moving till the first part hit, right?
Yeah.
So, but it looks like the second one at least has a constant acceleration.
Yeah. It was Logger Pro would if we moved a dot just barely, it would plot a velocity even though there wasn't one.
Because it's taking the derivative. And
Yeah. So the graphs were kind of confusing, but the big thing that we found was that the average acceleration of the middle point, negative mass, was negative 7.86, which compared to 9.81 was a pretty big error. But then we decided to drop the whole Slinky without it being stretched out and compare that. And its average acceleration was really close to that we found of the center of mass. And so we thought that could be due to air resistance just of the Slinky. So actually it was a lot closer to the acceleration we found for the center of mass. And then the last part is we compared it to a wave going through the Slinky as it stretched out, because Dr. Schuster gave us the idea of an information transfer. So a wave kind of would show that a little better. And we found that the graphs for these were incredibly similar to the top point of the Slinky, and which makes sense because that's the point that's sending the information. And it was almost exactly the same except for the wave was always a little higher. And so the only difference was this is only taken from the wave until it hits the center of mass. And after that, it got really funky. Like the acceleration slowed down a lot, and its velocity was really high in the positive, or well, really low in the negative direction, I guess, because it was a really high acceleration in the positive direction. And we thought that was because of the change in like tension past the center of mass, and the acceleration of the wave was also really close to the acceleration we found for the middle of the Slinky dropping and to the whole Slinky dropping. So all three of them were really close. So, yeah.
Conclusions. Okay, I'm gonna see that. So the bottom of the Slinky doesn't fall until the top reaches it. Like it just stands there. Anywhere on the Slinky doesn't move. So one of our conclusions is there's an information transfer, like the speed of sound or something like that. Like it takes time for the information or the drop to reach the bottom, and the tension remains the same, and it's equal to the force of gravity at the bottom. And it's equal to the force of gravity at the bottom, so it doesn't move until the top hits the bottom point.
This is the actual.
Wow.
But, basically, we thought that the center of mass was like the point of inflection on a calculus graph of like a curve, like where it changes from concave up to concave down.
This is the acceleration.
Yeah,
So,
acceleration.
so that's when it actually started accelerating upwards or slowing down. The fall started slowing because as it was going down, it was adding mass to it, and at that point there was, past the center of mass, there wasn't as much tension. So as it was adding mass, it actually ended up slowing down, which was the point of inflection at the center of mass.
And there was more mass in the bottom half because before it passes through the center, there's equal mass on the top and the bottom, but now it's being actually like compressed into the bottom half, and it loses the tension it had. And we thought that the acceleration is sort of like spread out throughout the Slinky, sort of. So like the top is moving faster than gravity and the bottom is moving zero, and that's why the center of mass is always an average of the actual acceleration of gravity on it, because every point on that kind of averages out to that. I don't know if that makes sense.
And then the center of mass of the Slinky, it had an average acceleration of 7.8, which was really close to the average acceleration of the whole Slinky without being stretched out. And it shows that the Slinky, as a unit, moves like the average acceleration of the whole thing is the same because of the tension on it. It's the same as just a regular fall, even though the top is moving faster than 9.81, it's counteracted by the bottom not moving at all. Yeah. In the middle of the Slinky didn't move until the top hit it either.
So this one is just talking about how it's like an information transfer, and it was just saying how the wave before the center of mass was the same as the top of the Slinky from throughout the whole fall. So we think that's because of the change in tension and like mass after it gets past the center. And that's it.
Do you have questions for these guys?
Let me see a video of the.
No, I don't have it. It's really fast. You can't really see anything unless you like slow down and go slide by slide.
So you're just holding it and then you're letting it drop? And seeing it
Well, no, you hold it and while it's already stretched out, like if you just hold it and it's hanging there with the bottom all the way
Just
down
holding
here,
the top ring.
and you drop the top ring, everything falls and compresses until it hits the bottom, and then it all starts to move. It doesn't
How do you
move
guys
right
find
away.
the center of mass? Like,
We counted the rings and then just put it at the center ring. So there's the same mass on both sides.
Did it change as the slinky was stretched though?
No, because we put a flag on the center ring, so no matter what, there's the same mass on each side.
so you were holding the bottom part so that the bottom part didn't move down?
Well,
No, wait.
No, we set it there, but then we moved our hand and then dropped it.
So the bottom part like levitates? So it's still
Yeah, it doesn't move at all. We watched a bunch of YouTube videos where they did like building sized slinkies and dropped them and they recorded the bottom and it does not move at all until the top hits it.
Oh,
And with the thing that other people hadn't pointed out is other parts of the slinky don't move at all either. Like if you look at the center of mass or any other point, it doesn't move until the top hits it, which is why it was important to talk about the transfer of information, because the message of the tension changing didn't reach that point until the top hit it.
The end. So it's like information being sent down, nothing knows, no part of the slinky knows that it's falling until the top hits it. So what we did was we just marked the top, the bottom, the middle, and then the 2 points in between. To understand why when you hold a slinky up and let go of the top, the bottom doesn't move. And we thought that the bottom would accelerate at 0 and that the top of the slinky would...
Which is actually not that one, it's this one.
Yeah. So basically we thought that the whole slinky would kind of be compressing throughout the fall, but we were wrong. Nothing on the slinky moves until the top hits it.
Pacific Islands, that's about it.
Are you recording?
I am.
Okay, Kevin, be quiet. So we did those on slinkies. No, just kidding. So basically we just wanted to be moving faster than gravity. We thought that the center of the slinky would be moving around 9.81 meters per second.
Because there was people on YouTube that said the center should move around 9.81.
Right.
That's the center of mass.